The basic idea of aliasing comes from the Nyquist Criterion. It states that the sampling frequency has to be greater than or equal to 2 times the maximum frequency. So this comes into play, for instance, when you're dealing with music. So if you're doing like sound recordings, no music or any recording of any sort has one pure tone. You have a ton of frequencies, and so you have to take that maximum recorded frequency and use that as your baseline for what sampling frequency you go at. If you've seen like TV shows or movies where they show a car driving and sometimes the wheels look like they're going backwards, that is actually because the frame rate of the recording is such that the tires are able to go not quite a full rotation before the next frame, and so it looks like it's going backwards instead, even though the tires are definitely going forward. Another example that is probably more important, especially for engineering's sake, is the idea of table saws. So table saws have to be calibrated to a very specific speed because the rate at which they rotate, it basically is close to an integer of the flicker rate of lights. And so that's a problem, because if the sampling rate were just a little bit off and it fell completely on an integer, it would look like the table saw is not moving even if it's on, which is very dangerous. You might think, well, yeah, but I can hear it going, but if you're in a machine shop, there's a lot of noises. And so they actually have to make the speed of the blade just a little bit higher than an integer. And so when I talk about the integer, I'm going off this F-alias equation. And so this alias equation basically says what the output frequency will be based upon the signal, or in this case the rotation rate of the blade, and then the sampling rate, and then n being some integer that you pick in order to make this whole right side of the equation as small as possible. And it can go down to 0, but it doesn't go negative because it's an absolute value. A visual representation of that on a graph can be shown with this figure on the left, where you see the top one is very highly sampled. It's definitely higher than the Nyquist Criterion, and so it's perfectly preserved, well, mostly perfectly preserving the sinusoidal pattern. But if we sampled much lower than that with the bottom one, we notice that the signal that the program perceives now has a much longer frequency, just because of where it's hitting on those along the path. The Nyquist Criterion only talks about figuring out the proper frequency, not the amplitude. And so we notice with this figure on the right that we've got the original signal given by kind of this greenish color, and then the alias signal given by the red. Now we're exactly hitting that 2 times frequency. And so we can see that the frequency is being preserved, but based upon where that first point is measured, we're not making it all the way up to that maximum amplitude. And so your signal is now at roughly 60% of what it should have been. And so you can imagine if we have more of those data points, that it'll become better and better at demonstrating that amplitude. There'll still be a little bit of leeway based upon when you take that first data point, unless you had an infinite number of points. There's always going to be a little bit of amplitude reduction. And I actually have a little Excel program that I put together to kind of demonstrate that. Here, what I have is basically a quick program that I put together that I can adjust a variable such as the signal, the sampling rate, and then what the time shift is. And I think I set the time shift to a random value. So every time I press something, it randomly generates another value. And here I demonstrate how much of that amplitude is being preserved and what that maximum voltage is. I just have a 1 volt amplitude input just to make the numbers come out easier. But here I'm exactly hitting that Nyquist criterion because my sampling rate is twice the signal. And so you can see this amplitude preservation is all over the place, ranging typically between 50% and 100, but here we hit 1.76. So this figure off to the right here is what it ends up looking like. And so if you happen to pick the wrong first data point, you can get basically a reading of 0 if you hit exactly the Nyquist criterion. So you don't want to hit exactly 2 times the frequency, you want to go much higher if you want to make sure that the amplitude is preserved. Now if I bring this frequency up to maybe 10,000, now we can see that range is much smaller. Now we're staying above 90%. And so now that's actually pretty reasonable. And if we go even higher than that, now, oh, that's not going to work because I have too many data points now. Let's see, let's try 30,000. Have to get at least 1 period, otherwise it doesn't work out right. So now we're staying within 1%. And so the higher and higher the frequency goes, the better the amplitude will be preserved. And so that's another consideration that you want to keep in mind when you think about the effects of sampling. Leakage is one of the topics that I find students struggle with the most. It's a little more abstract to understand, and there aren't really great examples of that in real life. There's a little bit, but it's not as easy to demonstrate in like a video or something like that. The fundamental equation we use for that is this equation here, n, which is the number of samples that you're taking, which usually is a power of 2 for a computer. So it'd be like 64, 128, 256, and so on. And then p represents number of periods. And so you want to adjust this sampling frequency and number of samples so that p is a whole integer. And the reason why comes down to this figure on the left, where we've got this actual signal given by the blue, and then we've got this measured signal, which we can see is just a little bit off alignment. So the starting point here is a little lower than the ending point here. And so what the computer does is it assumes that this whole batch is 1 period or 2 periods or something like that, some integer number of periods, and it constructs it like that. And so that's why we see when it makes this signal, we've got this little notch that's left over. And it preserves that notch all the way on through as it stitches that whole thing together. And when we look at the results of that, and this assumes a perfect signal, which isn't exactly a real thing, but if we had a perfect signal like this one, we would get a single amplitude at a given frequency if we take the FFT, converting it from the time domain to the frequency domain. And then if we focus on this version down here, where it's just slightly off, we end up getting the amplitude distributed to neighboring frequencies. Now, an important thing to know about this is that if you integrate over all of these frequencies, the total will still be equal to this maximum point for this top one. So nothing is actually lost. It's just basically not put into the right bin, if you want to think of it that way. Now, in a real system, there's always going to be a little bit of uncertainty with your frequency. And so you will always get some amount of leakage, but if you don't pick your sampling frequency and number of samples properly, that can be a much more significant contribution. And so you want to be wary of that when you're doing your sampling. So, Fourier transforms. I mentioned that just a moment ago. The basic idea is that frequencies can be added on top of one another. And so that's called the superposition principle. The basic idea of it is here we have 2 signals, and they're added on top of one another. And so we can see that we've got one larger frequency with a larger amplitude that's kind of following this path. But then we've got a smaller frequency that's kind of added on top of that to make it kind of more jagged. Fun fact, if you added enough frequencies at the right values, you could make this into a perfect square wave or something like that. You can make just about any shape if you pick the right frequencies to add together. So a Fourier transform basically takes this time domain information and converts it into frequencies. So it still has that amplitude. So we saw the amplitude of the first signal was at 1 volt, and we can see that it shows up here as a frequency of 1 hertz, and then another frequency as 12 hertz. And now it's much cleaner to understand. We know exactly which frequency inputs we've got, and say we wanted to remove one of those signals, like this one right here where it's actually a bit of noise. If we were to just completely remove that and take a FFT back into the time domain, now we've got this perfect signal where you don't have that jagged information anymore. And so that has a lot of applications for anything involving noise or unwanted signals in your system. Like I mentioned here, perfectly. Now this is an ideal situation where you can actually do that for the whole signal. Now that's a little bit harder to handle, so sometimes we use analog filters instead, which is a circuit involving a resistor and a capacitor. And you can use that to construct things like high-pass filters or low-pass filters, which follow these equations. And high-pass basically means it allows the high signals to pass. And then low-pass allows the low signals to pass, and it starts to cut into the other end of the frequency spectrum. Now, the problems with these filters is that it can actually reduce the signal you want to keep. Actually, it always reduces it. Sometimes it just reduces it to an acceptable amount, like maybe 0.1% or something like that, depending on what you pick your time constant to be. And also, it doesn't completely remove your undesirable signal. But it can reduce it pretty significantly based upon how you pick your filter. Now, digital filters is more like the example that I just showed on the last slide, where you actually take a Fourier transform, breaking up into multiple frequencies, and then you manually remove those undesired signals. This is very ideal as far as results go because you can just completely remove those signals. But there's some issues with that. For one, it can be very time consuming, especially if you're taking a lot of data. And then also you don't necessarily know what you want to get rid of and what you want to keep. Maybe you know a particular threshold, but sometimes there's another signal that you might not want, like maybe in addition to the 60 hertz signal that you'd want to remove, there's another one at roughly 20 hertz. And so just having a program pick out 60 hertz and remove that won't be good enough. It basically does a better job, but it also requires more effort on your part and the computer's part, which makes it non-ideal for certain applications. So here's a graphical representation of what I'm talking about, where we've got both the low-pass filter allowing the low signals through and cutting down the high signals, and the high-pass filter doing the opposite of that. Now this more, I guess, greenish-yellowish line represents the digital filtering. And so here we've got this clean preservation of your signal up on the left, and then a quick cutoff at whatever the frequency you chose was. Whereas the analog filter, given by this more bluish-greenish color, with that you see that above the cutoff frequency you do actually have a reduction of your signal. And a common cutoff point where we talk about is called this negative 3 dB point, or where it reduces your signal by 3 decibels. But you should know that even all the way here around 1 hertz, you're still getting a reduction of your signal. It's just very small at that point. And then this doesn't drop off to 0, it just continually drops smaller and smaller and smaller. Hopefully it's small enough to be negligible for your purposes. And here's the equation for gain. Typically there's a whole class dedicated to this, so I know I'm not doing it complete justice to it, but we only have so much time to talk about things.